what is the end goal for you, for your ideal solution? What do you want to achieve? How much autonomy do you want to achieve?
So I just described some of our work in autonomy. We use the same sensors at the high level control also for human-driven control. So as the patient thinks, those commands are directly sent to the motor, which then actuates the robot. So you can develop, say, for example, proportional myoelectric controllers, where there is a proportional relationship between the user's muscle activations and the torque output of your motor. Or in other words, as the patient contracts more with their muscles, the more torque you generate. So this way, there's no autonomy, there's no AI. The human is the intelligence. So we're not using artificial intelligence, we're using human intelligence, where the user is the controller. The user has volitional control over the robotic leg. Some people like that. There's actually a lot of research that suggests that that's actually a good thing. So there's no automation. It's the user has now agency over the robot. There's this sense of embodiment where if you have this type of control structure where there's no automation and the user using their own volitional control stemming from the brain, if those signals are used to control the robot, the patient is more likely to see the robot as a natural extension of themselves, as opposed to some foreign object. So my lab does both of these extremes. We're working to develop fully autonomous systems, and we're also working to develop fully integrated systems where just by the user thinking, they can control these robotic legs. We're also developing automation where the robotic legs can think and control themselves. So my long-term goal is to conduct the first ever clinical trials to be able to assess along this spectrum of autonomy, what level of control do individual patients prefer? Because it's most likely going to be on a patient-by-patient basis. And the best way to conceptualize what I just described is think of it in terms of autonomous driving. For maybe your listeners who don't know, there are levels to autonomy. There are levels to autonomous driving. Now, right now, most of your listeners, most people have experience with fully manual control. The user is in charge of the wheel. The driver is driving the car. Then there's fully autonomous, which we haven't achieved yet, where the car, you sit back and the car does everything for you. Now, people may think they like that, but how do you know? You've never been in a fully autonomous car. It doesn't exist yet. So there's a spectrum where there's fully manual versus fully autonomous. Different drivers, different passengers will probably prefer different levels of autonomy. And even for a given passenger, as you get more comfortable with the car, this autonomous car, you may want to change your level of autonomy. Or maybe on a given day, you're feeling maybe a little bit more adventurous. You want to use more autonomy or you want to use more human-driven control. We're doing the exact same thing with robotic legs. So right now, the automotive industry is looking at this and seeing what level of autonomy do individuals prefer. I'm doing the exact same thing, but for robotic walking. The problem is that these technologies don't yet exist. And so before we can get to those clinical trials, there's a lot of engineering and computer science that has to go into developing these controllers.
You're giving me some insight as to the trajectory that you will be taking. Unpack that a bit more for me. Tell me what the end goal is with that. So you're developing, you talked about, the underlying technologies behind the robotics that the end user will use. But there are multiple phases to getting there, of course, and the component technologies that are needed depending on what the intended solution will be. So talk to me about scalability. So you develop a technology, the ability to for I guess a prosthesis to be able to anticipate that you're going up the stairs. How does this solution, how does this translate? Tell me the path to getting to the user.
So it's not quite clear yet how this would look like in a commercial setting. We're not really there yet. And I may spend many decades developing this technology. It's really complicated when you're trying to interface with like the brain, and when you're trying to have humans interact with robots. It's very complicated, arguably more complicated than, say, automotive engineering or rocketry, because with those type of systems, they're engineered systems. We know their physics. We can just measure that. Can't really do that with a human. You can't disassemble a human and measure their physics. I guess you could after they've passed. We also don't really know much about its control. Like, we don't really know much about human control. We know about the control of rockets because we program them. We're the controller. We created the controller. With humans, we're still just trying to understand how to interface with humans in a meaningful way. It's a really complicated problem, actually. I'll likely spend many years developing these systems, again, ranging from fully autonomous control all the way to neural control using these interfaces that I was previously describing. From there, and we do a lot of work in simulation, like I mentioned. We also do a lot of benchtop testing. We do everything we can before any user touches our technology. And we're especially interested in and adamant about using computer simulation. It seems to be a growing tool that's used not only in academic labs like myself, but then also in large tech companies. So we do a lot of simulation and a lot of benchtop testing. From there, we then go to what we refer to as prototype user testing, often using my graduate students. And then from there, we can open it up to a larger research pool where we're testing with quote unquote able-bodied individuals. So these are persons without any type of disability. And that testing is often quite extensive. We want to make sure that we work out any kinks and that we are doing everything we can to ensure user safety. When you're talking about humans that are walking on robotic legs, this is a very serious thing, because if the robot makes a mistake, a person could fall down a flight of stairs. We do not take this lightly. So we do everything we can to make sure, even before we test on ourselves, like my graduate students, we do everything we can to ensure that we have maximum performance in simulation or on the benchtop. Then we open it up to, like I said, this larger pool. And once we're able to show a certain level of effectiveness and safety, we can then expand that, and we can start applying for ethics approval to be able to start testing with patients. And the technologies that I work on, two of them are robotic prosthetics and robotic exoskeletons. These are meant for individuals with various mobility impairments. I don't really specialize in a particular type of impairment. Robotic prosthetic legs, for example, also can be used by a number of people because amputation is very multifactorial. Sometimes people receive an amputation because of, say, war or some type of conflict. And we're seeing this, for example, back in my home country of Ukraine, where there's an increasing number of amputees because of landmines and missile strikes. And that's often what people think of when they think of somebody with an amputation. They think of war or some type of conflict. You'd be surprised as to how small a percentage that actually is. Or not a small percentage, but it's not the whole picture. I'll say that. There is an increasing incidence and prevalence of those with amputation as a result of diabetes and cancer. And especially diabetes, this is becoming a larger and larger problem with our aging population and with an obesity epidemic as well. And people often don't think about cancer, maybe unless you're Canadian, because one of the very famous Canadians, Terry Fox, died of cancer, and he had a leg amputation. This is a very famous Canadian, very well respected, and rightfully so. Now, his prosthesis was passive, which is fundamentally different than the ones that I developed. And nevertheless, so that's some of our work in amputation, or some of our prospective work. We're not there yet. So those are some of the patients we'd be recruiting, and we would be doing extensive in-house clinical trials with them under the watchful eye of a therapist, as well as a safety harness, just in case the robotic leg makes a mistake. We have the safety harness to be able to catch them. And this would go on for quite some time, several years. And then it's not even quite clear at what point and what does the end kind of product look like, where we then bring that out to a larger commercial pool. The other technology that you were describing, robotic exoskeletons. And so for people who don't really understand, like, what is this thing? When we think about prosthetic legs, they work in series with our bodies. So it's somebody with an amputation, then robotic prosthetic leg is in series. An exoskeleton is in parallel. Think of like an Iron Man suit or something like this, where it goes on top of the biological system, like a biological leg. This can be used to help assist and rehab somebody, for example, with a spinal cord injury or stroke, multiple sclerosis, cerebral palsy. It's a pretty extensive list, osteoarthritis. It also could be used to assist individuals just simply with muscle weakness due to aging. These devices also have the potential to augment otherwise healthy human movement. So again, this could be used by somebody like firemen, search and rescue, military, and that's often not discussed too much with these applications. But so the end users for those could be quite broad, actually, depending on the functionality and the purpose of the exoskeleton that you're designing. So that's like a little bit of kind of like the end users, you will.